period. I see you have an air mover? Some people, I see him laughing the reason I ask that, but people that own machines know that you got to always be taping up hoses, or you be on a job and you wear a hole in the hose, you got to tape it up, and it gets kind of crazy. In fact, I see right now I've lost my little plug that goes on this inlet, so I'll just put some duct tape on it, so I don't let air go in there. I need it going in one place. By the way, do any of you know how to use duct tape properly? When you get through, if you'll just take the end and do it like this, it's so easy to get it back off again. And that means a lot on some of these jobs where you're taping stuff up, rather than trying to find the end and peel it off. Okay, what we're going to do, we're going to load some perlite. You want to be my hose operator? I want you to just kind of slowly load it when we get going. Does everybody know what perlite is? Perlite's a very light material. It's used in insulation. It's used in the gardening industry to hold moisture. You see it in potted plants. Potted plants with perlite in it, but in the industrial industry it's used as insulation in butane or vessels to keep two surfaces at an even temperature. Let's just fire it off first to see if everything works. You hear that? How many of you guys here have air movers? Does that sound familiar? You've used, turn it off a second. You've used ADS hose, and it makes a whistling sound. This is a bilge pump hose, which is very similar to ADS hose. It's rough inside. This type of hose absolutely destroys the performance of air movers on long runs. I'm not saying you can't use it, but on long runs, the friction loss is incredible. It's just like this in the inside. And for whatever reason, it makes that whistling sound. This little model is a 1 inch equals to 1 foot scale, and I even got it tuned up so that the frequency is even identical in scale, believe it or not. Don't believe that one. But anyway, I'm going to let him load this material. What I want you to do is kind of load it and keep it above it so it kind of flies up in there. Okay. And watch what goes on in here. This has talcum powder and everything in it as well. You can hold it a little closer than that. A little closer than that. Can you load a little faster? Okay. Now, it'll load faster than that. Can you see what's going on? Did you see the cyclone spinning the dust out here? If you look over the bag outside, just keep going. Well, it's probably got stopped up. It stopped up. There's some big chunks there. There's some big chunks in there to get it occasionally. Yeah. Notice how the tank is clouded up. The cyclone is clouded up. But can you see how clear it is over here in the bag outside? There's some dust going through the bag out, or we wouldn't have a bag out. But it's designed to take the real small stuff out. But it's just loading right on up in here. I don't know. Can you see in the back how it's spinning the material out here? Stopped up again. We don't have to load it. I'm just trying to illustrate how the airflow goes. There's some real powder in there. You can see it, can't you, Carla? I'll try to see if it's loading up. That's good. We've seen the point. Okay, turn it off. Now you can see, if you look, the bag house is relatively clean. Very, very little material. And you can see what the dust that the cyclone took out before it came out of the top of the cyclone in the bag house. That's basically the principle work on. It's just what you see there. Okay, we're going to get these out of the way here. We're going to do a couple of demonstrations here on why hoses stop up. I guess one of the biggest problems in the air mover business with air movers is people stopping hoses up. Now, I'm going to do a little math up here. This might get a little boring to some of you. It was boring to me in high school and in college. Any of you remember that formula from high school? Area equals pi times the radius squared. I never thought I'd use that again, but I use it all the time today. This would be a 4-inch hose here. This might be a little bigger. This would be an 8-inch hose. Are 2 4-inch hoses equal in area to 1 8-inch hose? 2 4 is equal to 1 8-inch. 3 4 is equal to 1 8-inch. 4 4 is equal to 1. Too much. He says it's too much. So let's just figure that out and see how close he is to right. This is a 4-inch hose. This is an 8-inch hose. Area equals pi times radius squared. The radius of that is 2. The radius of that is 4. Okay? So this would be 3.14 times 2 squared. We know that this squared is 4. Is that right? Times 3.14 is 12 something. I happen to know what it is. It's 12.56. So there's 12.56 square inches in a 4-inch diameter circle. 12.56. Let's do the same thing on an 8-inch. That'll be 3.14 times 4 times 4. That is 16. 16. 16 times 3.14 is what? 48. You can see that would be 48. Actually, it comes out to 50.24. So there's 50.24 square inches in an 8-inch hose, and there's only 12.56 in a 4-inch hose. Well, what is that telling you? That's telling you that it's not only 3 times, twice as big. It's 4 times, almost 4 times exactly the square inches in an 8-inch versus a 4-inch. Now, why is that important? I'm going to tell you, it's probably one of the biggest things that people don't understand about air movers and what happens to them. What we're going to do, see if we can find the top there, Carlos. We'll do a little demonstration here.
What's that film?
This is the top for that thing there. We'll do a demonstration here. I need my little other hose back that's on that cyclone down there. Yeah, that one right there. Yep, there you go. Give him a guzzler hat. He's doing a good job. Put that hat on. Well, what I'm doing here might sound crazy, but it's not. It happens almost I guarantee it's happening somewhere right now. It's happening somewhere right now, what I'm doing, and somebody's doing it wrong. What I've done here is I've taken a 1-inch hose, 1-inch diameter hose, and I've reduced it to a 1/2-inch diameter hose. This is 1-inch ID, and this is 1/2-inch ID. This would be the same equivalency of what we did up here, taking an 8-inch hose and reducing it to a 4-inch hose. So what are we doing when we do that? Well, when we start out, this is the 1-inch diameter hose, 1-inch diameter shop vac. Now, I'm probably the only guy that buys a shop vac in Houston, Texas, and goes and reads the specs on a shop vac before he reads the instructions to see what the thing is capable of producing as far as airflow. This thing's 135 cubic feet a minute at 39 inches of water. Well, so what I've done, this guy that designed that shop vac says if I will build a machine, just like the guys at Guzzler or wherever, that moves X number of cubic feet a minute of air per minute, and I put it in certain size hose diameter on it, it should keep that material in the airstream at a fast enough or high enough velocity to travel through the hose all the way to the machine. The guy that designed this shop vac didn't think that Phil Stein was going to buy it and try to teach people how to operate vacuum trucks and do dumb things with it. He figured that, well, he's going to buy this machine for sucking up gravel. But what I did is reduce from 1-inch to a 1/2-inch diameter hose. And I'm going to start loading this. Now, you got to remember, when I start off, what is the air doing in here in this 1/2-inch in relation to what it's doing in a 1-inch? It's going a lot faster, isn't it? Probably not quite 4 times as fast. Probably more like 3 because of the friction loss. But it's really whistling. And I'm going to tell you, when you first start off on a job like this, that thing sucks. And I mean, it whistles. It can deafen you, literally deafen you on a job with ADS hose. It screams so loud. And you think you really got a machine. Now you go to work. But what happens when the air gets into here? Slows down, doesn't it? The velocity slows down. So I've got a job. I'm going to work. I got me a brand new guzzler here. I'm going to work, and I'm going to clean this pea gravel up. Turn it on, Kevin. Let's see what happens. Boy, I think man, I'm glad we bought this old guzzler. We're making money today. Well, It's kind of slowing down. It's not sucking very good anymore. Not like it was. Somebody call that guzzler guy and get him out. There's something wrong with this thing. It's just not sucking like... Well, I don't know what's going on. Turn it off. It's just not sucking good anymore. Well, this is a point in time whenever I get calls and you go out on a job, and have any ever seen guys out like this picking up hose and kicking it, shaking it, trying to get it unstopped again? That's what's happened to these guys on the job. They made a mess out of the job is what they've done. Well, y'all saw the pile of gravel I had there. That's all I got in the machine. Well, where is this stuff? Oh, I bet I know where it is. That's the same guys that's picking that hose up and down, kicking the hose and going crazy. So what I'm going to do is I'm going to put this thing back together if I can. Hook it back up. Now all I'm going to do to change this is I'm going to run the machine like whoever the engineer was that designed this machine to run it. He needed X amount of air going through a 1-inch hose. I'm just going to take this 1/2-inch hose off the end of it. That's all I've done. I haven't changed anything. And now I'm going to get the right amount of air through the hose to keep the velocity high enough. And hopefully, unless I really made a mess in here, it should clear itself out. Turn it on, Kevin. Let's see something now. Turn it off. There's the material now. And all I did was run a machine like this guy designed, or had it in mind when he designed it. Let the air go through the machine, let it flow. Let it flow, let it flow. This is probably one of the most common mistakes that there is in the industry. I'm not saying you have to use 8-inch hose on every job, or 6-inch hose, whatever the size of the machine. And I'm not saying you can't use 4-inch hose. I'm saying if you start off with, and you want to use 4-inch hose, take 4-inch hose all the way to the machine. If you take it all the way to the machine, it's not going to affect the performance of it. What happens is this acts like a trap. The air velocity drops so tremendously in a larger diameter hose, and the material just falls out of the airstream and begins to stop it up. And once it starts to stop it up, it just builds on itself. And I've seen people stop up hoses that you had to cut apart and throw away. It was so stopped up. You know, the cheaper ADS type hose. So keep it the same diameter. If you want 4, run it all the way to the machine. I'm not saying you can't run just a short piece off the back of that truck there and change it to 4, but don't run 8-inch hose 200 feet and then stick a 1-inch hose, a 4-inch hose on the end of it to last 50 feet. It's going to get you in trouble every time. Every time it'll get you in trouble. Can you start hooking that up? Yeah, that's all right. We're going to do another demonstration here. I'll have to get the hoses back here. I'm running. I've got a little valve, a little red handle valve somewhere that's laying up here. I kicked it around. You see it? There it is right there. I knew it was here somewhere. Okay. Need this jar. The big jar. Just like this. Okay. And I need to hook this up with that other little plastic deal. The little reducer. It's laying up here somewhere. Right here. No, it's right here. You heard me say earlier about inch of mercury. Well, I might not have got into the illustration. I'm fixing to get into it. Let me get by here. Yeah. Yeah, I'm going to have one of you stand up there. But it's going to be a second. I'm going to have to do some illustration. Okay. What is an inch of mercury? We hear us talking about inches of mercury, CFM, what have you. Hand me that green tape there now. There. Okay. If you look on that vacuum gauge I had earlier, it's rated in vacuum on one side and pressure on the other side, from 0 going this way. 1 inch of mercury. Hg is referred to as a sign for mercury. 1 inch of mercury will lift a column of water 13.3 inches. That high. In other words, if I wanted to lift a column of water With 1 inch of mercury, it would lift it 13.3 inches. If I wanted to have 2 inches of mercury on the machine trying to lift a column of water, it would lift it 26.6 inches, wouldn't it? 3 inches of mercury would lift it 39.9 inches. 4 inches, well, it starts to get a little complicated, the math, doesn't it, on how far. You don't need to know that it's 13 inches. Remember this, 1 inch of mercury will lift a foot of water, a column foot of water, because you're not always dealing with water. And why you or your operator should know this. Nothing looks more ridiculous than a guy on a job that's got a 20-foot suction lift. You got hose hanging down in a manhole or a pit or a sump or whatever. He's been running for an hour and a half. And you look over at the vacuum gauge on his truck, and his old vacuum pump won't produce but 12 inches of mercury. Well, he's only lifted the column of water up about 12 feet, and it's just sitting there static, isn't it? It's not going to go any further. If he had 29 inches, like this pump here, when it's in good shape, say 28 point something inches at sea level, he could lift a column of water, well, he don't do times 13.3. He could lift it about 29 feet, couldn't he? He could lift a vertical column 29 feet, probably about the height of this ceiling. So you got to remember this, that 1 inch of mercury will lift about 1 foot. On vacuum pressure pumps, 1 psi, 1 pound per square inch, if you looked at the other side of that gauge, would push water 2.31 feet. In other words, if you pressurize your tank for each pound of pressure, it'd push it up 2.31 feet. It'd push it about that far up. So 10 pounds would push it up, what, 23 feet? 20 pounds would push it 46 feet. You could push water 46 feet up in the air. You know, if you go to 25, you just keep doing the math. So those are two things you need to know. In some of the chemical plant applications we get into, they might want a bucket head, where they're trying to put pressure of one chemical or product into a pipeline that has 5 psi on it, where you're bucking the heads and you've got a differential there. So you need to know those kind of things. But in air movers, say you have to lift something 100 feet, or say you have to lift it 50 feet, and you've got a machine that only produces 15 inches of mercury, or maybe 18 inches, or maybe even a 29 inch or 27 inch machine. Well, how can you do this? What I want to do here is a little demonstration. I'm running out of time. I'll have to cut it short here because they want me through. I'm going to do a demonstration. This little fan, when I read the specs on it, was 39 inches of water. Come here, Kevin, hold this here. I want you to hold this up right here. Hold it down in the water. So when I turn that